Right, so hi, I'm Ashim Gupta. I'm a PhD student at Queen Mary University of London, and today I'll be talking about nonlinear Horndeski analysis with HiCOLA. So let me first start by talking about where we hope HiCOLA fits in. So lambda CDM has been shown to hold to high precision in solar system tests and things like that. But as good as it is, there are a few reasons why one might consider modified gravity models. So these are deviations from GR, modifications to it, to address various problems. Now, this has already been talked about. Theo talked about a few of them, but there's the cosmological constant problem. So the constant driving accelerated expansion that we get from data doesn't really match the vacuum energy one can calculate from quantum field theory. It's a huge mismatch. So that might be evidence that perhaps we don't really understand what dark energy is. Another one might be H0 tension. So the value of H0 we infer from Planck data and Schu's data don't match. And this mismatch is not supported by lambda CDM. So one might think perhaps lambda CDM itself might be the problem here. So that might be why someone wants to study modified gravity. So modified gravity theories with screening mechanisms, and they've just been mentioned in the previous talk, they are candidates that are consistent with, say, point 1. So the screening mechanisms they possess pull their behavior back towards GR in regions like the solar system. So they're okay with point 1, but they have differences in behavior on other scales so that they can perhaps deal with point 2, very shortcomings that lambda CDM can't. And screening mechanisms are typically terms, say, in your action that manifest on nonlinear scales. You won't see them if you only consider linear perturbations of your theory. So you need to go to nonlinear scales to actually see it and study it. And so HiCOLA is a fast approximate simulation package that I've developed alongside Dr. Bill Wright and Dr. Tessa Baker, also Queen Mary, for theories with screening that are valid on mildly nonlinear scales. And we hope that we can use that to compare with upcoming galaxy survey data to constrain this theory space of screen theories. Right, so, okay, what is HiCOLA? So HiCOLA stands for Horndeski in COLA. So let me now talk about what COLA is. So COLA stands for co-moving Lagrangian acceleration. It's a hybrid n-body code. It uses Lagrangian perturbation theory on large scales and an n-body part on small scales. And the marriage of the two gives mildly nonlinear results in less time steps than traditional n-body codes. So it's less computationally and temporally expensive than your usual n-body codes. And we can use COLA, we can incorporate and compute predictions for theories with screening mechanisms by encoding modified gravity as a fifth force effect. So here I've taken a figure from the original paper where COLA was introduced by Tassif and others. And you can see here that COLA in 10 time steps is able to give results that are quite similar to Gadget, which is an n-body code. And that takes 2000 time steps. So I mentioned that HiCOLA is designed to work with theories with screening. So which theories in particular is it designed for? So it works with Horndeski theories, Horndeski theories being scalar tensor theories. They are theories that add an extra scalar degree of freedom that GR doesn't have. That's represented by phi in this action here. In particular, we work with reduced Horndeski action. So this is where the gravitational waves in these theories travel at light speed. And we do that because of the constraints coming from GW 170817. So just to very quickly talk about the action here, the red piece is your GR-like piece. You have your Ricci scalar, you have your conformal scaling of that with the G4 phi. You have a yellow piece here. This is a nonlinear interaction term. And this is one of the ways a reduced Horndeski model can have screening. The self-interaction term will suppress the action of the scalar field on, say, solar system scales, and that's what pulls us back towards GR. And the important part here is that HiCOLA has been designed to be applicable to any model that is described by this action. So it's designed to be quite generic within this quite large model space. So K, G3, and G4, they're all free functions that need to be specified in order to reach a particular point in the theory space. So let's talk about what we've used HiCOLA to do. So perhaps I'll talk about something that perhaps is familiar to some people, and that's the Cubic Galileon. So to get the Cubic Galileon, you can make the choices for the Horndeski functions shown on screen for K, G3, and G4. And you can see that there are a number of curves on screen. These are for Cubic Galileons with differing initial conditions. So the F and EDS on the legend that you see here, these are related to the initial conditions used to generate these Cubic Galileons. So let's have a look at these, the background data. So let's start with E. So that's what we've been calling the Hubble function in our work. So you can see here that, and the black dashed line is lambda CDM. So you can see here that the cubic Galileons have the same kind of behavior where the Hubble function decreases over time, as we expect. And the agreement is pretty good at late times. So that looks decent. Again, omega radiation also falling, quite like lambda CDM, and at late times there's good agreement again. Omega matter, you can see that there is a period of matter domination in the cubic Galileon. It's a bit different from lambda CDM, but it does have the general feature of having matter domination. And again, at late times, there's decent agreement, and then there's some differences here and there. And as matter drops, you can see that the energy density of dark energy increases. So that we're getting the dark energy domination that we see today. And in this case, dark energy is composed of both a cosmological constant and the scalar field. So it's omega lambda and omega phi. I should note that one of these curves, the sine curve, corresponds to when omega lambda is completely turned off. So HiCOLA is capable of having only scalar fields as a dark energy component. But you can see here that basically these cubic Galileons have the right kind of qualitative behaviors that are lambda CDM-like. So let's have a look at the power spectra of them. So this is what we get. First of all, I should state that these power spectra are plotted relative to GR. So here we're just seeing how the cubic Galileon differs from GR. And you can see here that they all have linear enhancement on large scale. So that's on the left side of this plot. They all have these kind of scale-independent linear enhancements. Then the deviations grow up until reaching a peak, and then they start to fall again. That fall is screening in action. We're seeing that yellow box term coming into effect and suppressing these deviative effects of the cubic Galileon and bring us back towards GR. And that's what makes these theories look like GR in regions where we expect them to. Something we're able to do with HiCOLA is we're able to break down that power spectrum and understand what is giving rise to that shape. So to understand what constituent parts are responsible for that. So what we do is we isolate various effects. We can isolate, for instance, the effect of only the expansion history. We can also isolate the effect of only the screening term. So you can imagine comparing this with, imagine if you had a cubic Galileon without screening. That way, the deviations would run unchecked. It would never have been pulled back towards GR. So we can isolate that efficiency of screening. Today, in the interest of time, I'll just focus on the top left one, or just draw your attention there. This is the effect of just the background. So no fifth forces are responsible for this particular plot, but just the difference in expansion history is causing this difference between the cubic Galileon and lambda CDM. And you can see that the full modified background is quite significant. For the sine curve, for instance, it can go up to about 25%. So what we've seen from HiCOLA is that there is a great importance to actually consider the full modified background and not just assume that it is just exactly lambda CDM, even though they're quite close. Now, I said that HiCOLA is designed to work with a wide class of Horndeski models. It's generic. So let's talk about something else then. So another model we've looked at are these extended shift symmetric models. And these are studied by Trakova and others last year. So to get these, you can make the choices that are shown on screen. So it's like the cubic Galileon, but you have these extra x squared terms. These models have this feature of being very good at showing expansion histories that look a lot like lambda CDM. So this one can match lambda CDM even better than the cubic Galileon can, right? But let's have a look at the power spectra. So here what we're seeing is that even though their expansion histories look really close to lambda CDM, they still have pretty visible differences at the level of the power spectra. You can see that the green ESS model has differences of up to 7.5%. So what we're saying here is basically that even if you apply constraints on ESS models so that their expansion histories look a lot like lambda CDM because of various constraints experimentally, they still have the capability of showing different behaviors on other levels like the power spectrum. So there's this kind of richness in theory space here, a potential to explore. And again, just like in a Cubic Galileon, we have the same features of linear enhancement. There's a peak, and then the screening activates and pulls us back towards GR on smaller scales, towards the right of the figure. So my takeaway messages are, first of all, I've just introduced HiCOLA. It's a numerical package that produces fast, approximate nonlinear matter power spectra for a wide class of Horndeski models. And we hope that this will enable the first tests of the Horndeski family on nonlinear scales with surveys like LSST. We've also seen that through our usage of HiCOLA, that including the modified background is important as its effects are significant on the power spectra. So it might not do to actually assume that the background is like lambda CDM. You should consider the full modified background. And we've also seen that even if you choose your models such that they show very lambda CDM-like behavior, there are still visible differences at the level of the power spectra. So there's this potentially rich theory space to study and also to constrain using galaxy surveys, because you can't just see it with expansion histories, and you need power spectra to actually see where they are different. And I'll just say that we're writing a paper that discusses everything I've talked about and more. So if you're curious about how HiCOLA works and what we've done with it, please stay tuned. Thanks.
Great, thank you very much for giving us that overview of HiCOLA. We can take a minute for questions if anyone has anything they'd like to ask now. There's a question that's come in on the chat from Stefan. Let me read it out. How strong are observational constraints on the entire expansion history of the universe, i.e. does it need to match Slander's EDM well?
Right, so that's a good question. It's one of those things that we've asked ourselves that would help us with trying to find models. So obviously the Cubic Galileon had, for instance, 2 model parameters and then all those initial conditions. The ESS models have 4 model parameters, and so let me just show you what I mean by that. So the ESS model, for instance, has K1, K2, G31, G32. These are all constants that have to be fixed somehow. So in one sense, the more constraints we have, the better it is for fixing these things. And what I'll just say is that what we have so far is we have a lot of constraints near today, right? We know what omega matter is today, we know what omega radiation is today, et cetera, And in fact, HiCOLA is designed to work backwards. The initial conditions actually set today, and it solves backwards in time, so that we can use the data we have today. So this is really an open question that we actually hope to research more, which is how many constraints do we have in order to actually constrain models that we can study using HiCOLA. The more we have, the more we can actually constrain these model parameters and initial conditions, really. So we purposely picked to go from today backwards, but it's an open question really for us, which is, do we have anything early, like CMB data? Can we use CMB data as well to perhaps constrain this? Yeah, it's an open question that we hope to actually see very soon.